Hello students, welcome to the fascinating world of inorganic chemistry, a branch that is often underrated, sometimes feared, but truly one of the most beautiful and foundational pillars of chemistry. Many students think that inorganic chemistry is all about memorizing reactions and periodic trends. But let me tell you, it is much more than that. Inorganic chemistry is the language of elements and the architecture of matter, and it's the blueprint of nature, how it constructs the molecules, minerals, materials, and every matter around us. Once if you start visualizing three-dimensional structure of molecules, the way atoms bond, the geometry they take, the spatial arrangement of orbitals and electrons, it no longer becomes a dry theory. It becomes an exciting visual science, almost chemistry in 3D motion. During my teaching journey, I have visited many schools, interacted with many students and teachers. Many of them started visualizing this inorganic chemistry as a matter of symbols. For example, I have asked one of the kids, how will you explain hydrogen molecule formation from its constituent atoms? For example, one hydrogen will combine with another hydrogen to form H2 molecule. Then immediately he replied, sir, one H is here, another H is here, both H are moving and it forms one covalent bond and it forms H2. Means he visualized as a matter of symbols. But in real world, hydrogen exists as a system. I mean, it's a proton and electron around it, right? So that atoms, when they're combining, and there will be proton and electron attraction forces, that's how bond will generate. Means when you start visualizing, when you start learning inorganic chemistry, the symbol has to disappear and systems has to appear, and the electron and proton interactions and then spatial arrangement of these electrons around those atoms, how stable structure it is bringing, how stable bond it is bringing, how that interactions are developing. All these things makes more interest and it creates a lot of excitement for the kids towards learning inorganic chemistry. Let's together break this myth that inorganic chemistry boring and tough. Believe me, with the right mindset and approach, inorganic chemistry can be your most scoring and enjoyable subject. Let's dive in. Let us consider this type of inorganic questions, right? It's a typical JEE question. How to solve this kind of questions from the fundamental, right? So if you observe this question, it is mostly involved in N2H4, N2F4 structure related, right? So they are asking select the incorrect statements about N2F4 and N2H4. So before going to discuss about this question, you must know certain fundamentals in inorganic chemistry, like one of the most important fundamental, which is bent rule. Today I am going to discuss about one of the most fundamental concepts in inorganic chemistry, which is bent rule. Once after learning this bent rule, you can able to identify bond strength and bond angles and how percentage of S character in hybrid orbital will influence bond strength and bond length. We are going to discuss in detailed way. Let us start bent rule in detail. Before going to discuss about bent rule, let us discuss and let us understand the three-dimensional structure of a molecule, and if central atom is surrounded by different substituents having different electronegativities, how that redistribution of hybrid orbitals takes place in a molecule. Let us discuss and experience clearly. Let us consider a molecule CH2F2 and understand how that sp3 hybrid orbitals are redistributed, where percentage of S character more, where percentage of P character more, and how that bond angles will change during this redistribution of hybrid orbitals. Let us experience. If you see this molecule, three-dimensional molecule, and let us consider C, and here fluorine, and here fluorine, and hydrogen, right? So now we know fluorine is more electronegative, which will pull that electron clouds. Means this lobe sp3 lobe size will be little bigger compared to this sp3 lobe, which is oriented towards the hydrogen. Why, sir? So whenever fluorine is more electronegative, which is pulling, then the electron clouds will be shifting away from the carbon. It is towards the fluorine. So directional character will increase. Means the spherical thing, if you imagine this is the sphere and somebody is pulling the electrons like this, and this will extend its, and then this S character becoming to P character. Means the non-directional character of the orbital becoming more into directional, more towards the fluorine. That's how percentage of p character will increase for CF bond compared to CH bond. If you consider CH bond where hydrogen is relatively less electronegative compared to fluorine, so it will be giving electrons towards the center, and then carbon will hold that electrons, the common pair of electrons, the bond pair of electrons will hold towards the center. So the hybrid orbital will start shrinking and it moves towards its nucleus, and we know whenever electron, this lobe size, the electrons are shrinking towards the nucleus, percentage of S character for that hybrid orbital will increase. Finally, the conclusion here is, here in this case percentage of p character will increase, and here in this case percentage of S character will increase. Meaning whenever central atom surrounded by a different substituents having different electronegativities, the p character, percentage of p character towards more electronegative atom will increase, and percentage of S character towards of less electronegative atom will increase. This is what Bent stated, and which will be a crucial parameter for us to understand the bond strength and all. Let us see how the bond angles will change. Let us visualize the same concept into this picture also. For example, this is the carbon central atom, and if you consider more electronegative atom fluorine, it starts pulling the electrons, right? So when it starts pulling the electrons, and this lobe size will increase when you compare with hydrogen. So this hydrogen is less electronegative, or you can say electropositive relative to this carbon and fluorines. So now what will happen, this cloud, this particular lobe becomes smaller. If you consider CH lobes are smaller, CF lobes are bigger, right, as we discussed earlier. So you can visualize the molecule like this also, right? So now let us move how the bond angles will change. For example, this theta 1 is the bond angle between HCH, and theta 2 is the bond angle between HCF, and theta 3 is the bond angle between FCF. How this bond angle will get influenced by this redistribution of hybrid orbitals around the central atom. This is for those students who are feeling difficult to understand technical terms. Let us make it simple. Let us consider a person who is present at center of the tetrahedron, right? So who is surrounded by 4 different people, right? Out of that, like, let us consider one person who is sitting at a terminal positions, means who is known as substituent fellow. If that substituent fellow is more electronegative, means who is having a capacity of pulling electrons, the common pair of electrons or bond pair of electron towards itself, right? So now when he starts pulling, the electrons will move, the bond pair of electrons will move away from the center. Means whenever electron pair is moving away from the center, p character will increase. Similarly, you consider another person who is flexible of giving electrons to the center. So now he is pushing the electrons towards the center, or otherwise you imagine, so this central atom can able to hold his electrons from this person. Means that lobe hybrid orbital size will get contracted. I means that bond pair of electron will penetrate towards the central atom. The lobe size will decrease, percentage of S character will decrease. Like this also you can visualize. Here we have to make 2 important conclusions regarding bond angle and bond length, which is going to make a huge impact on overall structure and reactivity of a molecule. We know when percentage of S character increases, bond pair of electrons will move more close to the nucleus, so that bond length becomes smaller. Similarly, when you consider percentage of p character whenever increase, the bond pairs moves away from the nucleus, whose bond length will increase. Regarding bond angles, if you consider, whenever percentage of S character increases, as bond pairs becomes closer, if you observe in this structure, these bond pairs when they are moving closer to the nucleus, central atom nucleus, and whose percentage of S character will increase, they will become closer, and repulsions between this bond pair becomes more. When repulsions between these bond pairs increases, bond angle also will increase. Those two bonds will move away, so that bond angle will increase. Similarly, when percentage of p character whenever increases, the bond pairs are moving away from the center, means the distance between these bond pairs will increase, so the repulsions will decrease. Whenever repulsion decreases, the bond angle will also decreases. They will come closer, so it results decrease in bond angle. The overall conclusion about this concept you can observe in this frame. So if you see the relation between percentage of S character and bond length and bond angle, similarly percentage of P character, bond length and bond angle. Now we can find the relation between theta 1, theta 2, theta 3, which are bond angles between HCH and HCF and then FCF. So let us consider this. Here percentage of S character more, because of that bond angle will increase. So theta 1 will be the highest, and then here percentage of S character more, here percentage of P character, so it will be the next one, and then here percentage of P character more, so because of that bond angle will decrease, so theta 3. So theta 1 is greater than theta 2 greater than theta 3. Let us consider the CH2F2 structure in 3D model. For example, if you consider these white color things represents hydrogens, this is CH bond, and this red color things represents fluorines, CFF. Now let us consider these hydrogens are relatively less electronegative. So because of that, the central carbon pulls electrons. Because of that, percentage of S character for this particular bond will be increasing. Whenever this bond pair is moving towards the center, so it will be having a closer to each other, the distance less. Because of that, repulsion will increase. So repulsion increases means bond will move, these two bonds will move away. Because of that reason, bond angle will increase. So percentage of S character increasing and bond angle also will increase with this CH bonds. Now let us consider CF bonds. When you consider these two are CF bonds, where fluorine is pulling electrons towards itself because it's more electronegative. So percentage of P character will increase. Because of that, bond pair of electrons will move away from the center, both. When they are moving away from the center, the distance between the bond pairs will increase, repulsions will decrease. Because of that, these two bonds will come little bit more closer. So because of that reason, bond angle will increase. Means percentage of P character increasing, bond angle will decrease. Let us discuss one of the most common and fundamental example for Bentrol. That is, if you consider trigonal bipyramidal structure, you have two positions. One is axial position, which is perpendicular to the plane, and another is equatorial position, which is on the plane. Means you have a triangular plane, and above and below you have axial positions. Now when you have a mixture of two substituents, two or more than two substituents, which is having different electronegativities, the most electronegative atom will always prefers to occupy at axial position. So that we can explain logically also. This trigonal bipyramidal structure we can visualize as the combination of a trigonal planar structure, perpendicular to that axial positions are there above and below. So for example, the equatorial position, the triangular plane is formed by the combination of s orbital, px and py. So which leads to the formation of equatorial plane, which is sp2, and perpendicular to this xy plane, we know z axis. Along the z axis you have a pz orbital and dz square orbital, and they will be having this kind of orientation, and then on top of that you have dz square. So everywhere you have got this pz and dz square combination, which will be moving away and which leads to the formation of axial bonds. So it is a xy plane, triangular plane, perpendicular to that pz and dz square elongated. So along the axial position, so the percentage of S character almost becomes 0. Drago has suggested a relation between percentage of S character and bond angle, as well as percentage of P character and bond angle. For example, if you take theta is bond angle and cos theta is equal to S by S minus 1 and P minus 1 by P, where S and P exclusively participating. For example, if theta is equal to 90 degrees, then cos 90 is equal to S by S minus 1, cos 90 we know 0, so S becomes 0. Means along the axial position, the bond angle whenever becomes 90 degrees, automatically we can say percentage of S character becomes 0 and percentage of P character becomes highest, pure p orbital, where hybridization almost becomes negligible. That's what Drago suggested, that we can discuss separately as a different topic. From this, if you consider on equatorial position, bond angle is 120 degrees, means there is percentage of S character, and axial position when you take it, this angle is 90 degrees, axial and equatorial bond angle if you consider is 90 degrees, where percentage of S character almost be negligible. That's why in trigonal bipyramidal structures, in general, the axial bonds lengths are longer than equatorial bond lengths, because in axial positions percentage of S character less, due to that bond length will be slightly longer compared to equatorial bond lengths. For example, if you consider PCl5, there is always axial bond lengths will be longer than equatorial bond lengths. However, there is a typical case PF5 where axial and equatorial keep shuffling. It's called pseudo rotation, which leads to equal bond lengths per PF bond. This is a separate thing which we can discuss. One more important point regarding bent rule is, so the lone pair of electrons always prefers to occupy a hybrid orbital with more percentage of S character. Whenever a hybrid orbital with more percentage of S character will be close to the nucleus. If you keep the lone pair of electron close to the nucleus, the force of attraction will increase. Whenever attraction increases, potential energy will decrease, system becomes more stable. Let us consider an example, PF2Cl2. If you consider PF2Cl2 structure, so phosphorus hybridization is sp3d. As usual, there is axial positions here and equatorial positions, right? So in equatorial positions here, percentage of S character is relatively higher side. So because of that reason, percentage of S character is high. Whenever percentage of S character high, it becomes more close to the nucleus. Phosphorus can attract that lone pair strongly. System becomes more stable. Similarly, here if you consider fluorine is more electronegative atom. More electronegative atom always occupies axial positions. Why it is axial position? Because more electronegative atom will take bond pair away from the plane and directional character will increase, and whenever bond pairs moves away from that plane, repulsion also will decrease, system becomes more stable. That's why more electronegative atom always prefers to occupy axial position. Till now we have discussed about the redistribution of hybrid orbitals according to the electronegativities of the substituents around the central atom. Now we are going to discuss about what is the exact statement given by Bent and Bent rule. This is a basic statement given by Henry A. Bent. In chemistry, Bent's rule describes and explains the relationship between orbital hybridization and the electronegativities of substituents, which we discussed. The rule was stated by Henry A. Bent. So the atomic S character concentrates in orbitals directed towards electropositive substituents. Means whenever substituent electropositive, central atom can hold that bond pair of electrons close to nucleus, and that's called as percentage of S character increases. And a central atom is bonded with to multiple groups will rehybridize so that orbitals with more S character are directed towards electropositive groups, and orbitals with more P character will directed towards more electronegative elements. Also the lone pair prefers to occupy in an orbital with more S character. Right? This is what the example. Let us consider, this is one of the most common question asked in many entrance corners. Let us discuss in detail. For example, let us consider two compounds PCl3F2, PCl2F3. So which of these compound is polar? So if you consider PCl3F2 or PCl2F3, both the cases phosphorus undergoes sp3d hybridization, which forms trigonal bipyramidal structure. Now, but locations when you consider, for example, if you consider here, it is PCl3F2, let's consider PCl3F2. As we have already discussed Bent rule, according to the Bent rule, more electronegative atoms should be present at axial positions in trigonal bipyramidal structure. So you have a chlorine and fluorine. Obviously, fluorine is having more electronegative. So because of that, like fluorine occupies axial positions. Remaining 3 equatorial positions were occupied by chlorine. So here, so this axial position, fluorine is pulling above this direction and then this is below, right? They'll get cancel each other, the dipole moments. And then this resultant of these two will be projecting towards this direction, and whose magnitude, if you take it, it will be same, and the other CCl is pulling opposite directions, both will get cancelled. Finally, dipole moment for this thing becomes 0, means which is a non-polar compound. Right? Similarly, you can consider PCl2F3. In this case, as usual, fluorine being a more electronegative element will occupy axial positions, and remaining positions you can keep it chlorine and fluorine. Now these two will get cancelled, but resultant of this thing will be, it's not same as the other thing, because here you have fluorine and resultant of these two chlorines will give again PCl thing. So mu is not equal to 0, dipole moment not equal to 0. So that's why we will consider this compound as a polar compound and this compound as a non-polar compound. So many times they ask which of the following cases dipole moment becomes 0, and that is PCl3F2, and its non-zero dipole moment means PCl2F3. Another most important fundamental is, if percentage of S character in hybrid orbitals whenever increases, the bond length will decrease and bond strength will increase. Here if you consider sp percentage of S character more, because of that whose bond strength will be more, and sp2 which is greater than sp2 which is even in turns greater than sp3 in hybrid orbitals. This is about bond strength. This is which you need to understand one thing, and this is related to bond strength. So if you consider here one important note, many of the students asked me the same doubt. Sir, we know that percentage of S character increases and bond length will decrease, bond strength will increase in hybrid orbitals. But in many of the books they mentioned that SS overlapping, if you consider, which is less efficient than SP overlapping, which is less efficient than PP overlapping, and it's less than PD overlapping. So which case it will be true, sir? So both are true. In case of atomic orbitals, when they are undergoing simple overlapping of orbitals rather than hybrid orbitals. For example, two hydrogen atoms when they are combining, pure s orbital will combine and it forms bond. So during atomic orbitals, yes, this is true, SS overlapping less than SP less than PP less than PD, because whenever S character increases in normal atomic orbitals, the atom want to retain its electrons close to nucleus, whose participation in the overlapping region or bonding becomes less, due to which the electron density in the overlapping region becomes less. So this concept is exclusively for non-hybrid orbitals or simple atomic orbitals. So what we are discussing in compound the central atom undergoes hybridization, then you have to apply SP overlapping greater than sp2 greater than sp3. This is what the most important thing. Now let us consider one important example here. So if you take it CH3 and CF3 what will be the bond length and strength of CC in both the cases? In which case CC bond length will be higher, and in which case CC bond becomes stronger. Let us compare and analyze it. So now if you consider CH3 here, because whose electronegativity is less, so electronegativity is less means percentage of S character here increases. Here it is more electronegative, because fluorine is pulling, percentage of P character will increase. Whenever here percentage of P character increases, CC, if you take it, percentage of S character will be more. Here percentage of S character more, then other bond percentage of P character will increase. So due to which, so bond length if you consider, A bond length is greater than B. This is in terms of bond length. Then what is bond strength, sir? If I consider this molecule is 1 and this molecule is 2, bond strength, CC bond strength if you consider, 1 is less than 2 in case of CC bond strength. Hope you understand this example. Let us solve this wonderful question by using all the fundamentals whatever we have learned till now. For example, here they have given select the incorrect statement about N2F4, N2H4, right? So they have given two compounds here. One is N2H4 and another one is N2F4. Let us analyze the structures first. Let us take N2H4 first. N2H4. This is N2H4. The structure of this is, let us consider this is nitrogen and you have a lone pair of electrons here, and here you have hydrogen, here you have hydrogen, and then the third place again one more hydrogen. So now it will be two more hydrogens will be inverted mode, and this lone pair exactly opposite to this, because two lone pairs whenever stays away from each other, the system becomes more stable by experiencing the less repulsions. Now when you consider this, these are the hydrogens you have, right? And these are the lone pairs. Same thing if you consider for N2H4 structure. Instead of hydrogens, you have to replace with fluorine, N2F4. So now you have a nitrogen, same here, and you have got fluorine, here fluorine, and then again here nitrogen, and then these fluorines will be inverted, and this lone pair exactly projecting downward direction, which is opposite to this. Now when you consider this fluorine, as we discussed already, here this fluorine is more electronegative, right? So more electronegative. Whenever more electronegative atom is there, which starts pulling the electrons. When starts pulling the electrons moves away like this. It will be, so percentage of P character will increase for NF bond. Whenever one particular bond percentage of P character increases, another bond percentage of S character. One is stretching, another one will be shrinking. So here, if I am taking this particular NN bond, will have a greater percentage of S character. Here percentage of P character will increase, here percentage of S character will increase in hybrid orbitals. Similarly, when you take it here, this hydrogen, so which is less electronegative compared to this, so electrons are moving away. So like here, I mean from hydrogen, so nitrogen holds the electrons tightly here. So here what will happen, percentage of S character will increase, and then here percentage of P character will increase. Whenever this percentage of P character increases, which leads to whenever percentage of P character increases, so you know already bond length will increase. Whenever bond length increases, you know bond strength will decrease. Bond strength will decrease. Similarly here, percentage of S character in hybrid orbitals, it is increasing. Means here we discussed already, bond length will decrease and bond strength will increase. Whenever bond strength is increasing, bond energy also will increase. So when you see these observations, and you can solve that question quite comfortably. For example, let us consider this question based upon this. Select the incorrect statements about N2F4 and N2H4. So first statement, in N2F4, d orbitals are contracted by electronegative fluorine atoms, but d orbital contraction is not possible in hydrogen atoms in N2H4. So which is completely wrong, because both the cases you don't have any d orbitals. Neither hydrogen nor fluorine has got d orbitals. So there is no question of d orbitals contraction. So first statement incorrect. And the next, the NN bond energy in N2F4 is more than NN bond energy in N2H4. So we already discussed, as fluorine is pulling the electrons and P character of NF bond will increase, and which like increases percentage of S character in NN, percentage of S character NN whenever increases, bond length will decrease, bond strength will increase, which we discussed already here in this clearly, right? So here we discussed percentage of S character increases because fluorine is pulling electrons here, and this bond will get shrinking here, and because of that bond length will decrease, bond strength. So NN bond becomes more stronger in N2F4, so it will have a greater bond energy compared to N2H4, right? So here the second statement is correct, and the NN bond length in N2F4 is more than that of N2H4. It is wrong because in N2F4 fluorine pull whenever it is increasing, so percentage of P character will increase NF, NN bond percentage of S character will increase, so bond length will decrease. So this is wrong. And then the NN bond length in N2F4 is less than that of N2H4, like that they are saying. It is the NN bond length in N2F4 is less than that of N2H4. Yes, percentage of S character more. So you have two statements incorrect, the first one and third one. So the B is correct answer. Like that you can explain, you can solve the questions, these theoretical questions by using the fundamentals. Let us also compare the OO bond lengths and OO bond energies in H2O2 and O2F2. The most peculiar question they kept on asking in all entrance corner. Let us discuss slowly and pleasantly by applying the fundamentals. For example, you consider H2O2. The structure we know already, hydrogen peroxide structure, OH bond here and then OH opposite, and of course two lone pairs will be there, right? So we will compare this thing with O2F2 structure. For example, instead of these hydrogens, I am replacing hydrogens by fluorine. So let us consider two fluorines you have. So they will consider this bond length is A and this OO bond length is B. They are asking the relation between A and B. Which bond is shorter, which bond is longer, like that. So when you consider this, we have already discussed here oxygen hybridization is sp3 hybridization because two bond pairs, two lone pairs. Now when you consider this fluorine which is pulling electrons, so which is more electronegative, whenever there is a more electronegative atom, this is a more electronegative, this is a more electronegative, because of more electronegative nature, and this lobe size will increase and P character, percentage of P character for this bond will increase. Once the neighboring bonds percentage of P character increases and it stretches more and this bond becomes shorter. So here percentage of S character obviously will increase. Whenever percentage of S character increases, bond length will, as we discussed already, bond length will decrease and bond strength will increase. Bond strength will increase. So when you consider this is lower electronegative, so it means like you can say electropositivities compared to oxygen. So the electrons will become closer to this and it will be moving towards the oxygen, where percentage of S character will increase in OH bond, and then obviously the center bond OO, if you consider, percentage of P character will increase. Whenever this percentage of P character increases, bond length will increase. Bond length will increase. So we can conclude that A is greater than B. Means the bond length of oxygen in H2O2 is longer compared to O2F2, means OO bond length in O2F2. We can also apply the same concept in case of alkynes, alkanes. We know alkynes are more acidic compared to alkenes, and which are more acidic compared to alkanes. But let us analyze why it is so. So after losing hydrogen, say acidic strength basically depends upon the stability of the conjugate base. Means once if you remove that H plus ion, the conjugate base should be more stable. So in case of triple bond, what will happen is, once if you remove this hydrogen, you will get a triple bond carbon getting negative charge. I mean, like here, the lone pair of electrons present on triple bond carbon whose hybridization is sp, where percentage of s character is 50%. So, which is more percentage of s character, more close to that nucleus, means the lone pair becomes more closer to the nucleus. For example, if you consider here, in case of triple bond, the lone pair are close to the nucleus. In case of double bond, little bit away. In case of single bond, it becomes even stays away from the nucleus. So, triple bond carbon attracts lone pair strongly because of more percentage of s character. So, whose stability becomes more. That's why alkynes becomes more acidic compared to alkenes and alkanes. Let us discuss another important application of the concept in inorganic chemistry, and which are most common questions they are asking in all entrance corner. So, which is percentage of s character of lone pair is inversely proportional to basic strength. So, we know Lewis basis means the electron pair donors, means the strength of basicity depends upon the ease of donation of lone pair of electrons, right. So, now if the lone pair is present in s orbital or like percentage of s character more, then it will become more closer to the nucleus, means nucleus attracts those lone pairs strongly, whose ease of donation to the outside outside element, it becomes difficult. So, that is how basic strength will decrease. Let us discuss some example regarding this concept. Let us compare basic strength of NH3 and NF3. Right. So, here in these two structures, if you consider this hydrogen is electropositive relative to nitrogen, means these electrons will be moving close to the nitrogen. Whenever they are moving close to the nitrogen, I mean here this bond becomes shorter and percentage of s character will increase, in which case NH bond, whenever they are moving close, automatically they will start repelling this lone pair of electrons, which will move away from the center, means here the lobe size will increase, means the lone pair of electrons moves away from the nitrogen nucleus, means here percentage of p character will increase and percentage of s character will decrease, means that as s orbital rather than spherical shape, because of these lone pairs, these bond pairs which are coming closer, which will push these electrons little away. So, in contradiction to it, in NF3 case, fluorine is pulling, right? When fluorine is pulling here, if you consider fluorine is more electronegative atom, because of more electronegativity, so percentage of p character here will increase because electrons are moving away. Even you can compare bond angle also. When percentage of p character increases, bond angle will decrease. Almost NF3 close to 90, we will say that in NF3 case hybridization almost becomes negligible. These are all called Dragos concepts or Dragos compounds. Now, so when these bond pairs are moving away from the center, means towards the fluorine they are pulling. So, automatically this lone pair of electrons, these are lone pair of electrons, will be moving little bit closer to the nitrogen. So, whenever it is moving closer to the nitrogen, percentage of s character will increase, means the lone pair will be attached to the nitrogen nucleus more firmly. So, whenever percentage of s character increases, then basic strength here will decrease. Means in these two basic strength, if you compare, NH3 has got a better basic strength compared to NF3. Let us discuss one more basic important inorganic trend. Even they have given this thing in NCERT book, which is a very important for all entrance corners. Let us consider ammonia, hydrates of fifth year group elements. For example, you consider NH3, PH3, ASH3, arsenic, and antimony, SbH3. So basic strength they will ask you, right? So in this case, if you take it, NH3 can react with even normal water to form ammonium hydroxide, means it can receive the H plus ion. PH3 which only reacts with hot water, means basic strength of NH3 is higher than PH3, which is greater than even ASH3 and SbH3. So why it is so, sir? What is the reason for this? So we already discussed about this. The basic strength will depends upon the ease of donation of lone pair of electrons. When you take it NH3 here, NH3 here, and then PH3 you consider here. So here in NH3 case, this nitrogen is pulling electrons, right? More electronegativity of nitrogen. Because of this, bond pairs will come close to this nitrogen and it will repel this lone pair. Whenever it repelling that lone pair, whose like lone pair will move away from the nucleus, and percentage of p character will increase, and which can able to donate that lone pair easily, because the lone pair stays away from nitrogen nucleus, right? So it can donate easily. But whereas when you consider this one, so relatively this bond pair moves away from the center, because phosphorus is relatively less electronegative compared to nitrogen. Because of that, this lone pair almost remains into s orbital only, whose hybridization also negligible. So, right, so this will be moving towards the center little bit closer way. So you can say here, one second, I'll just explain this thing, and you can consider this is closer to the nucleus, and then what will happen is percentage of s character will increase. Whenever percentage of s character increases, phosphorus nucleus will start attracting the lone pair of electron. So displacing that lone pair of electron from the system becomes difficult. That's how this basic strength of PH3 becomes less. Thank you.